Okay, here's our sheet of metal over here that is 56 feet in length and 21 feet in width. And we're going to cut equal squares out of each corner, fold up the sides along these dotted lines to create an open box. And we want to know what the size of X should be to create the box, open box of maximum volume. Okay, and the idea is that if this length is 56, then this length right here is 56. Take away 2 x's, these little pieces of the square that get cut out. And similarly for the width, this width is 21 minus 2x. When I fold up the box, the height of the box will be the size of the square. So that's what the box looks like, and there's a formula for the volume right there. Now, how are you going to find out what value of X generates the maximum volume? Well, I didn't see this problem posed under the calculus heading. So if you're not using calculus, you have to graph the function and locate where it hits its maximum, which is right here. This is a graph of this V right here. We've restricted the size of the square to be between 0 and 10.5. If you're equal to 0, you won't have cut out any squares and you can't create a box. And if you're greater than or equal to 10.5, you'll use up too much of the side to also create a box. So by graphing, there is the value of X that generates the maximum volume. Now, if you're using calculus, you would want to find the derivative of V, which would be this thing right here, and you want to know when does that equal 0. So, well, before I tried to solve this, I noticed that every term was divisible by 4. And then I found the prime factorization of 3 times 294, and eventually figured out that I could split the middle. This is negative 77 into 63 and a minus 14. And I was able to factor this, solving for X without using the quadratic formula. So this is what you end up with, 3x minus 14 times the quantity x minus 21. There's your answer right there, 14/3 or 4.666666 repeating. We reject the x equals 21 because that's not in the domain of our function. To prove that that generates a maximum, we could use the first derivative test, find out that 4 2/3 was the critical number. So to the left of 4 2/3, like 1, v prime of 1 is positive. So the function is increasing, and that's what this picture shows right here. And to the right of 4 2/3, like 5, the function is, the first derivative is negative, so the original function is decreasing. That's what this shows right here. Also, on Desmos, if you create the function v of x equals this 4x cubed minus blah, 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 you can then on the next line type v prime of x, and that's what this red graph is, the derivative of the original function. And when that crosses the x-axis, that's where the first derivative equals 0. So there's your 4.667 confirmation. And over here I've got a table of x values and the v values that they generate. And there's your 14/3, which looks like it does generate the maximum in this list, confirming everything that came before. There you go. Hope that helped. If you have any questions, post a comment.